All right. Welcome back, everyone, to summer lecture number 3. This is going to be an introduction to reinforcement learning and AI. My neighbor's getting their roof done, so if you hear some noise, that's what that is. Hopefully you can hear it. If not, then you probably won't see this. Okay, so let me just get started real quick with a little bit of history, right? So, Um, basically, the history of AI is really interesting. You kind of see these patterns of AI winters. So you have periods of time where there's just no real work getting done and not a lot of scientific contribution. And that's just because many different reasons, but mainly it's just because of either it's just a lot of people just did not think it was feasible or if it was tractable, and a lot of other people just felt that their time or attention was spent on other fields that had a little bit more promise. So in 1958, right, Frank Rosenblatt, who I believe was a neurophysiologist, so he's coming from more of a biological and like psychological approach, not really from computer science kind of frame of mind. But he came up with a perceptron, which was just a single layer kind of linear network of physical sort of neurons, which we'll talk about. But this was built on physical device, and so it's kind of limited, right? Like how big you can make these is just kind of limited by how tiny of the neuron, how tiny like the size of neurons you can work and you can't have like a bunch of neurons because you have to make those by hand. So that's kind of and then you have a little bit later from that you have Marvin Minsky and Seymour Papert, who were a couple of people at MIT, and I believe they were mathematicians, but they proved that these perceptrons are great, but they can't really do nonlinear problems. And so an example of that is something like XOR, where it's not exactly like input output, right? There's a little bit of a logic behind that, and so these perceptrons, their network just could not sufficiently handle any complex problems. And so that was like the first real AI winter, right? So with this paper that Minsky and Papert like produced with this textbook, actually, most of the research kind of just slowed down. And then about a decade later, right, you had this whole computer, revolution, and you had personal computers, and you had the compute really scale up, by like 2 orders of magnitude around. And so people started to get back into this, and you had hot field networks, and then backpropagation by Geoffrey Hinton. And so this backpropagation paper was huge because here you had multiple layers of perceptrons, and you had non-linearization, and you had this backpropagation kind of concept, which was relatively simple, and you kind of see that it is relatively simple. But this really spun up a bunch of research and interest and investment. And then 1990s, Jan LeCun created the convolutional neural network. And so this convolutional neural network was used to recognize handwritten digits um, with the post office. So if people's handwriting is like really bad, he used these CNN to recognize handwritten digits on the labels. So that was huge. And then in 2012, I think it's sort of the last thing I mentioned, AlexNet, which was this really large convolutional neural net, used GPUs, graphical processing units, and this showed that like if you sufficiently scale up these neural networks, they will give you really great results. So AlexNet was a network to recognize like a bunch of different categories or a bunch of different images. So it should be able to recognize like dogs, cats, objects, cars, like everything. And so they used this CNN approach, and they won this competition called ImageNet by around like 10%. So they improved the state of the art by 10% with this. And people thought like this was a crazy result. And it's crazy to me because hey, like you don't have to do anything like fundamentally apart from just scaling it and adding a bunch more GPUs and scaling up the network. And so with this, you sort of get into deep learning and deep neural networks. And so this is where I think the field has kind of taken us to now and to today. That's a little bit of the history. Um, and then what we're really interested with robotics is reinforcement learning. So reinforcement learning is like a piece or like a field of AI, and its kind of theme is learning without discrete labels or immediate feedback. So with a lot of these other sort of methods and a lot of these other fields of AI, it's more so, hey, we have a bunch of this data and we have it labeled. So like we know what this data means, we know like the result of this data. So for example, right, like you may have an image and you say, hey, this is an image of a dog, right? The fact that you know the dog for them know that an image is a dog is really important because if you have, 10,000 images of dogs in different angles and different photo like angles and lighting means that you can train an AI system to classify an image as a dog. So having this kind of label associated with your data is really important. And so reinforcement learning, you don't really have this specific label. And you also don't have immediate feedback. So, for example, right, Andrew Ng, who is a really popular and really famous computer scientist, his work is in reinforcement learning. And so his PhD thesis and some of his work is with controlling helicopters with reinforcement learning. And so what's interesting is, right, a decision you make when flying a helicopter may not have an impact immediately. It may take a couple seconds, right? May take 10 seconds for that decision to really affect the trajectory of the helicopter. So again, if you don't have immediate feedback or if there's not any discrete labels, then reinforcement learning is kind of an interesting or somewhat a useful technique to try and apply. And especially if you're dealing with sort of time data where it's like, you have kind of a series of steps that go from, t equals 0 to like a minute, then that may be another indication that reinforcement learning is suited to your. Okay, so now we want to talk a little bit about terminology. And this is important just that when we kind of frame these problems and we um, we talk about like states and observations and trajectories, this terminology that you sort of just understand what exactly we're talking about. So let's get started. So um, we have ST, right? Mistake. Um, So ST, right, stands for whatever the state of the world is at a specific time. So state of the world at time t, for example. And so t could be anything. It could be like, but it's usually like at the present moment. Now, observation is what, an agent or what a person observes at time t. So the difference between state and observation is state you can think of as the complete ground truth. And so what this means is it contains like all of the specific values, contains the entirety of what's going on. So for example, if you're like driving down a highway, right, inside a car, the state is not just, the velocity of your car, but the velocity of the other cars on the road, how the wind is moving, how the other cars on like the other side of the highway may be moving, how the trees are moving, is kind of it's kind of like a theoretical approach. It's like theoretically this is what the world is doing at this time t. But your observation is mostly what's used kind of with these RL systems, but it's what you observe. So this could be your velocity relatively how the cars around you are moving. So you don't know their exact velocity, but you may know that hey, they're moving faster or slower than me. So that's your observation. So it's not the truth, it's just what you observe. And that's kind of an important distinction. Okay. Next is action, and this is, the decision that you take at time t. So again, going back to this driving car analogy, right? Your action at a specific time is, hey, am I going straight? So am I like, putting my feet on the accelerator? Am I braking? Am I turning left or right? And how much am I turning? Or am I just like doing nothing. Whatever it may be, those are your actions. And so actions can be either like discrete, so it may be like, hey, I'm going to brake completely, right? Or it may be continuous. So it's like, oh, I'm going to brake like 30%, or I'm going to hit the accelerator like 10%. So for that one, there's like a whole range of values or a whole range of actions you can take. So you have discrete and continuous actions. That you don't really need to know too much about, this discrete and continuous, but I think it's just somewhat important for you to kind of sense what what sort of actions our robot has to take. So for that, it's going to be continuous, right? Because the motor it can control only the motor positions, and those motor positions can be anything, right? Um, they can be between 0 and 2 pi radians, or whatever the limits of the motors are. So those are kind of continuous actions that I can take. Again, trajectory, we represent it with this tau symbol. So it goes from 0 to t, and it's just a pair of um, whatever the state is at that time and the action at that time. And then again, another state. Okay, I'm just going to continue. And another action. And you just continue it to state at the end time and action at the end time. So that's a trajectory. And then you have a reward or a reward function. So the reward function just says how good is this specific kind of state and action pair. So if you're driving down, again, if you're driving down the highway and your car, if you turn suddenly left, or sorry, turn right directly into the car next to you, then you would want your reward function to throw off like um, throughout the results saying like this is not good, you're making a horrible decision, like this is not a good state in action to be in. If your car is flipped upside down, then purely based on that state alone, you would want the reward function to say, this is not a good state to be in, and you're getting zero reward for this. Like it's not good. Okay. So uh the whole kind of framing of our problems is with this Markov decision process. And sort of what that looks like is given a state and an action, right? Those two things are the only things that contribute to the next state. So it's kind of a simplification because obviously there's still like randomness and like stochasticness in the world around us. But with this MDP Markov decision process, we sort of just assume that the next state is only dependent on um, previous dependent on previous um, states in action, previous state in action. So um, it's just a simplification that we make, and it sort of works well because you can't really add this like stochasticness of the world to this model without really complicating it. So again, more formally, it's just like the next state is purely a function of the current state in action and randomness. So they do like take it into account, but it's just sort of hard to you know actually code that in. So um, the next state, right, is only dependent on the previous state, not the state before that. So what this means is like state three is only dependent on state two and action two. It's not really dependent on state one. Okay, so that's NDP Markov decision process. Really, it's just again like what that means is just like a simplification that the next state is only dependent on previous state and action. Okay. So the goal of reinforcement learning is to maximize the reward that you get over trajectory. So again, trajectory represents this tab. So over t equals 0 to time t, whatever it may be, um, what you would want is to maximize the reward you get from that. So you would sum up the rewards at each of the time steps. So you would sum up the reward from state at time 0, action at time 0. And then you'd go and you would sum up all the way to the reward at state time t equals capital T and your action at time equals capital T. So at the last time step. And so the way you sort of do this is just by picking the best action given the state. Because really the only thing you can control is what your actions, in this case. And so how do we decide what the best action is? That's what your policy does. So we represent policy with pi, but your policy should be able to figure out what the best action is given the previous state and previous action taken. So again, states are the ground truth, and so you may not have access to that, right? You may only have access to whatever you observe. So in that case, again, it's just going to be the same thing, but it's just going to be based off your observations. So this would change the equation a little bit, but like, again, if it's a bad observation, it's a bad observation. So if your car is flipped upside down, right, that observation is a bad observation. So you should be able to say like, oh, like the reward function should say this is a terrible observation. Whatever actions you took in this trajectory are terrible actions. You gotta change your policy a little bit. And so you take an action by sampling from your policy. So this is a little bit tricky, but essentially the way these RL algorithms kind of work is your policy spits out a a bunch of different options, and each of these options have a different probability. So, for example, right with the driving thing, we may say, hey, take a left, or take a right, or continue straight, or brake. And so your policy will say, hey, we think 80%, we have 80% confidence that this left turn would yield a good reward. And then like 10%, I don't know why that keeps happening, guys, but 10% for taking a right turn, 5% um, for taking straight, and 5% for braking. So when you sample from this, right, um, like kind of a Gaussian kind of sample, then um, this left turn would have a really high probability of being selected. And so that's just kind of how these models work because they're inherently kind of probabilistic. So they only deal with probabilities. So the way you kind of pick an action is just from sampling what the policy has the probabilities of the certain actions maximizing. And so you observe the next state, and that's usually you do this by kind of modeling the world dynamics and sort of sampling from the world dynamics. So again, it's kind of tricky, but you essentially say, hey, given current state and the current action, right? What sort of is the what does the next state look like? And so that's sort of what this is about. And so you get this trajectory, um, you know, with state in action, and the next state in action, all the way up to the end. And you call this sort of trajectory and like executing them a policy rollout or an episode. So that's what that is. Okay, now we're going to talk a little bit about neural networks, lag, or like the spiking. So now I'm going to talk about kind of how we actually do this. And so the first sort of building block are neural networks. So what exactly are neural networks? You can think of them as just really fancy function fitters. So given a bunch of inputs, they give out a bunch of outputs. So it's simply a function. Um, but the thing is, the number of variables can kind of be a lot. So I believe, don't quote me on this, but I believe like the latest Claude model has 10 trillion parameters. So that's a 10 trillion variable function, kind of. So that's kind of how you can think of it. And so in essence, the way they sort of work is computer scientists look to the human brain for inspiration, and they found, our neurons had sort of connections going in and connections going out, and they were connected to other neurons. And then these neurons could be connected to each other, and they would also be connected to other neurons. And you'd have a bunch of these packed together in certain regions of the brain doing different things. And so they sort of looked at this and they kind of simplified it and adjusted it to um, what we have now. And so this is, you can think of it really as just, again, a fancy function, but as just doing weighted sums. And so we'll get more to how this works and how this looks like. But the last thing I want to say is the perceptrons were pretty much just up till here. So perceptrons, what they did was you would have a bunch of these neurons, and you would have one output neuron, or maybe two, depending on how complicated your thing is, your model. But you would have, this was not what it was supposed to be. But you would have kind of a weighted average, and then you would spit it out an output. So these were sort of the simple perceptual networks that people were talking about with Rosenblatt. And so with those MIT mathematicians who kind of wrote the paper that, hey, this doesn't really scale well, we'll see why it doesn't. And and so this is just what they're talking about. Okay, so I just want to frame in mind kind of what exactly we're trying to do. And hopefully, like with this thinking, you can sort of understand neural networks a little bit better. So today we're talking about MNIST, which again was this collection of handwritten digits that Jan LeCun used a convolutional neural network for to try and recognize the digit. We're not going to use a convolutional neural network or a CNN. We're just going to use a plain neural network, regular NN, and we're just going to use this network to try and recognize handwritten digits. So the way we do this, right, is first the handwritten digit is 28 by 28 pixels. So 28 times 28 is 784, and that is the number of pixels. So what we do is we feed in all of these pixels into our network. So we create a neural network, which I'll talk about like exactly what this comprises of. But for now, just worry about this column, and this is our input column. And so each kind of pixel will be in its individual node. So each pixel gets a node. And so whatever the value of this node is the pixel value. So say, right, that we sample this pixel, right, the top left, that is black, right? That's completely full black. So that is going to have probably a value closer to 0, right? And then if we sample here, right, that is a white pixel. So that pixel is going to have a value closer to 1. So all of the pixels in this image will be between 0 and 1. They may not be like exactly 0, because if it's 0, then the input doesn't matter because it's 0. So maybe like 0.1 or 0.01. But you feed these pixels and their pixel value into all the nodes, right? And so you can think of those as your inputs for this function, right? So again, function would be your pixel values. And and so what should this output, right? What's the eventual output? Well, we want it to output what the handwritten digit is. So function given pixels should give some number between like 0 and 9, right? Um, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In our data set, there's no like image with a handwritten 10. And that's because a 10 is just a 1 and a 0. So now, how exactly do we do this? Well, again, I mentioned kind of earlier with the sampling from the probabilities that we sort of deal with probabilities with neural networks and like conventional approaches. So what these output neurons should do is their output, again, they can also output a value. So you can think of it as like a multi-dimensional function, right? Where you have given x and y, right? You get a z. Well, what if you had like, you know, x, y, and z, and you get, two outputs, right? You get v and w, right? So if you keep on going, you can kind of see how this works as a fancy function figure. But um, this output node can output probability, right? A percent chance that the network thinks that the image that you fed it in the input is this digit. So for a fully accurate, kind of trained model, you would want, for example, the output node corresponding to the digit 0, right? The digit 0 is not 9. So you would want this to say a really low probability. So you want it to be like, 5 or 10%. But if you feed this image, which is a 9, right? You want the node corresponding to a 9 to be really high. So 0.41 is decent, right? You'd want it to be kind of greater than 50%. So then you kind of sample from this and you kind of realize, oh, the model is kind of confident that you gave it a sorry, the model is pretty confident that the digit that you gave it is a 9. So that's kind of what our system that we want to set up should be able to do. And so again, if these are your pixel values and it's 28 by 28, and so you can feed them like each pixel value into the network. Okay, so what exactly do we want our network to kind of do, right? So the first thing I want to mention is with these neural networks, it's kind of a black box. And so you hear this kind of a lot. Sorry, it's not a blank box. My bad. It's a black box. It's a black box in that you don't know what's going on inside the hood. Like you don't know what exactly the network is doing to give you these probabilities and to be accurate, right? Like for us, right, if we look at the digit, we can sort of say, I know it's a 9 because of like this kind of long edge in this loop, right? I know this is a 4 because it has this sort of straight edge, but it also has this shape and there's like a gap in the middle. Whatever it may be, like we sort of have like a more like algorithm and we can sort of explain things and I'm thinking a lot better. With the neural network, it can't. Like we don't know what's going on in the middle. Um, we only know like what we feed it and what we get out, but we don't know how it's come to any of the conclusions it's come to. And so there's a lot of work going on to make explainable neural networks, but I just want to emphasize like we don't exactly know what's going on, so it's kind of black box. But what we'd want to imagine happen is like it's kind of parallel to how we think, right? So, for example, you feed it the pixels into the input layer, and then um, the structure of a neural network is that you do some computations in the middle, and then you have another set of neurons, and then you do some more computations, and then you have another set of neurons, and then you do more computations, and this time you have an output set of neurons. So maybe, right, our our network will say, okay, we've got a bunch of pixels, right? Maybe in this computation block, it will kind of recognize like shorter segments of the digit, right? So maybe if we draw like a 9, if you feed it a 9, it'll say, oh, I kind of recognize like sort of like the makeup of this 9, like sort of abstractly. And then we do more computations. So hopefully those more computations will sort of piece together those sort of smaller segments into something a little bit more abstract. So with Xenon, we sort of split it up a bunch of times. Maybe we'll say, oh, we've got like a loop and we've got a line. And then you have another set of computations here. So maybe these set of computations will sort of understand that, oh, a loop and a 9 makes a 9. Like that means like the digit 9. That's what the humans mean. Say when they say 9. And so maybe then we'll say, okay, we think this is a 9. So that's what we think may happen, but we don't exactly know. That's just like an interpretation. But you can think of sort of the way the neural network works as kind of an analog of this, where it's like you feed it a bunch of inputs, it does some computation, it gets like a little bit closer to the end result, does a little bit of computation, it gets a little bit closer to the end result, does a little bit more computation, and it gets a good result at the end. Okay, so exactly how does this work? Um, so I want to keep the math a little bit to a minimum because it kind of blows up kind of quickly. Um, but I'll keep it as simple as I can. So say we have a couple neurons, right? We'll say we have 3 neurons. And so let's feed it different values. And so let's feed 1, 2, and 3. So this neuron has a value of 1, this neuron has a value of 2, and this neuron has a value of 3. Then, right, what happens in this is we want to propagate information. So we have like the current kind of state of the neuron, but we want to propagate information. And so the way we do that, we want to propagate information to like another set, the next set of neurons. And so the way we do that is we form connections, right, between the neurons. So each neuron is connected to each other. And then we pass sort of weight associated with this connection. So for example, right, I'm just making up numbers, but say um, we have 0.2, 2, and this so we have these like the input values, and these are sort of the current state of the neuron. We pass information, and we pass sort of the importance of that information with these weights, and we call these values weights. So again, just to make things a little clearer, right? Because this diagram's a little bit crowded. Um, if you have a neuron and you send it to another neuron, right? You have value of the neuron, which will says 1, and you pass weight, so 0.2. And then if you have another input neuron, right, and this has a value of 2, and you pass information, right, you need to pass the importance of that information. So you may say it's 0.3. Again, the 0.2 and 0.3 are kind of arbitrary, but just for your understanding, right? And so now we can sort of do some computations, and we have data, and we have like information about that data being propagated, being like linked together and being kind of networked. And so what do we do with this? Well, we need kind of a value for this neuron, right? As we propagate information, right? Like this neuron should kind of represent the information that's gone from previously. Um, so from these two. So what we do is we take a weighted sum. So what is a weighted sum? Well, it's just um, the inputs times their weights added together. So let me try and color code this a little bit better. So 1, 2. So it's 1 times 0.2 plus 2 times 0.3. So that's going to be 0.2 plus 0.6, and that's going to be 0.8. So this neuron is now going to have a value of 0.8. And so the same thing happens if we add another neuron. So if we add another neuron, right, we would need to create new weights because there's no connections between this input neuron and um this neuron. So we need to create a weight here and a weight here. Just reverse the color theme so it's just clear. But I'm using this. Okay, so now, right, the same thing. So what is the output of this neuron? Well, it's again a weighted cell. So it's 1 times 0.3 plus 2 times 0.2. So that's going to be 0.3 plus 0.4, and that's going to be 0.7. So this is going to have a value of 0.7. And then again, like a network is just comprised of these sort of calculations again and again. So now we have 0.8 and 0.7. If you want to make connections to the next layer of neurons, is going to be the same sort of logic and the same flow again. So we may say 0.1, 0.2, 0.3, and then make some more connections. And we have the weights, and it's going to be the same calculation as before. So that is kind of how information and like the state of the neurons gets sent to the next layer of neurons. So what I mean by layer is if we look at this image, um, we call like the set of neurons like stacked together like this as a layer. So this would be an input layer. This would be a hidden layer, and it's called a hidden layer because it's between the input and the output. So it's kind of hidden to like what people really interact with, like what we interact with. So we send in inputs and we get outputs from it, so we don't really interact with the hidden layers, right? So we'll call this hidden layer, and this is we'll call this hidden layer 1, and then we'll call this hidden layer 2. And then this layer is our output layer, right? So again, it's just these sort of computations repeated layer to layer. Okay, there is one bit that we need to cover, and then I think we're going to be mostly done with word propagation. So again, with that perceptrons, right? We had these weighted sums, and that was it. But we sort of have a problem in that it can't really solve nonlinear problems. So what do people do? They add a non-linearization term to this. And so what they do is um, they take our weighted sum, which I'll just call weighted sum, and put it into a non-linearization function. So yeah, I'll talk more about what this means, but you take your sum and then you use it as input to a non-linearization function, and then that is your final output. Okay, so what exactly does this mean? Well, just more concretely, right, there's this function called the sigmoid function. So if you look at what the sigmoid function is, right, uh, it looks like this. And so you can see that's non-linear in that it has like a curve to it. And so this is what like the function is, 1 over 1 plus e to the negative x. And so what you do is you take your input and you feed it into this function. And so looks like this, right? Whoops. Yeah, okay. I don't know what I was trying to draw there. Um, right. Okay. So you feed it into this function. And so if it's a negative number, it will be closer to 0. And if it's a positive number, it will be closer to 1. And so the function is 1 over 1 plus e to the negative x, right? So you take your weighted sum, and that's going to be your x, and then you get this output, and that's going to be the final output, and that's going to be the value for your neuron. And so the reason you do this again is to add some non-linearity. Because without it, right, it would not be able to solve really complex problems. Because a lot of the computation kind of requires just like non-linear thinking, kind of. Again, that's kind of like the intuition behind it. It's just you need to add a little bit of complexity, and you need the fancy function fitter to be able to handle non-linear aspects of whatever problem you're trying to solve. And so you need some sort of non-linearity, and you do that by just passing it into whatever function. So there's other functions that this is the sigmoid that we talked about, but there's also the ReLU, which is rectified linear unit, and there's a couple others like GLU, Gaussian rectified unit maybe. But sigmoid is what you'll see mostly for beginners. So that's the workflow, and what that looks like is we sort of want this to be in matrix form. So again, to draw out this network one last time, right? So you have your inputs here, and then you have your weights here. So if you do sort of the computation, right, if this was an input of 1 and 2, and then this was 0 0.2 and 0 0.3, right? We do 1 times 0 0.2 plus 2 times 0 0.3. And then you do the sigmoid list. So what that looks like is a matrix of your weights multiplied by a matrix of your inputs. So you have 0 0.2 and 0 0.3 multiplied by 1 and 2. And this is a matrix multiplication. So if you do the matrix multiplication on this, right, you would have a 2 by 1 times a, did I do that right? No, sorry. I'm all over the place today. So 1 by 2, right, 1 row, 2 columns, and then you would have 2 rows, 1 column. And so this would be a 1 by 1. And that would be, again, 0 0.2 times 1 plus 0 0.3 times 2. Okay, so then we can do our sigmoid over this matrix multiplication, right? We could do the and then like symbolically that's the sigmoid over the weights times the inputs. Now there's one thing I sort of left out, and that's the bias. So with the bias, right, essentially what this does is it increases or decreases the activation required. Decreases activation. Okay, so what I mean by this? Well, let's look at the sigmoid, right? If your weighted sum is a negative, right? So if it's like negative, right? But right, that is going to contribute not a lot of value to your network. But let's say like, hey, this is a really important sort of neuron, right? This -4 means that like it's some really important information, and this should really count to the network. Then you want to add some sort of bias to it, say like 6, to kind of push it this way so that it has a higher activation or a higher value at the end of the sigmoid function. So at the end of like, the final output and towards the value of the value of the neuron. So again, like if it's -4, but it's like, hey, this is really important for you to like consider what this means, then you can add bias and then you can shift it to be positive, and so um, then it has a higher activation value. And so activation value is just like the final value of the neuron. And so if this was like a 6, for example, usually the activation values are like between 0 and 1. But just for example, right, if the activation value was a 6 and all the other neurons are like 0, 1, 6, 2, then this neuron has a lot of say. It contributes a lot to that weighted sum on the next layer. So yeah, if this was 6, 1, 0, 2, and you do this weighted sum, this sixth one, no matter like the weight, right, is going to carry a lot of weight. Is going to carry a lot of significance. So that's kind of the feature of the bias. And it also works both ways, right? So if you have a value that's +2, but it's not really as important, and like a +2 doesn't really mean anything, then you can add a negative bias and shift it to the left. So then it will be closer to 0, so maybe like 0.5 as its activation value. And that means like, okay, it's not going to contribute anything. Like this neuron does not have a lot to say in the conversation of like, what the neurons are talking about to each other. So that's kind of the point of the bias. And so the bias is just subtraction. So what that looks like is you just add a bias. So in this case, we only have one value, so we may add like whatever the bias may be. So you leave it as like y equals mx plus b, right? With this b kind of shifting up and down the activation value at the end. And then symbolically, right, that's just you have weight times your inputs plus your bias. And then you feed that into your activation function, or sorry, your sigmoid function to get the actual value. Output value, and then activation value. These again mean the same thing. So I think that may have been a little confusing, but I hope I can walk through an example, and as I continue to, it may just make a little more sense. So let me just walk through a quick example here, right? So let's say we have two neurons, their input value is 1 and 2, and then you have one neuron here that you're trying to calculate the value of. And then also just to get a sense of like what the next neuron layer will look like, let's say we have another layer, another neuron in this second um, layer. And so actually I'll just add another output here, another neuron here, just so it makes a little bit of sense. Okay, so 1 and 2 as your input. So 1 and 2, that's like the value of the neurons. Then let's start making these connections. So let me try and make them kind of small. Yeah, perfect. So each of these neurons is connected to the other neurons in this layer, and each of these is connected to this layer. So this is our input layer, guys. This is hidden layer 1. And let's just say that this is our output. Okay. So now let's say that this neuron connected to this neuron has a weight of 0.2. This neuron connected to this neuron has a weight of 0.4. This neuron connected to this neuron has a value of 0.1. This has a value of 0.2. So again, each neuron is connected to every neuron in the next layer with this connection. And each connection has a weight, which is like the importance of that neuron's input. Okay, so if we were to calculate this, right, we would have the weights, which would be 0.2, and let me just make the colors make sense. 0.2, then 0.4, and then 0.1, and 0.2. So those are all. And then we multiply by our inputs, which is 1 and 2. And then we need a bias. And so the bias is going to be for each of these neurons. So plus a bias, plus a bias, plus, we'll say bias 1 and bias 2. Then we take this and let's call this variable z. And z is going to be a matrix with two values, right? And so we'll do sigmoid z. So again, let me just walk this through one more fully. So let's say that um, one sec. No, okay. Um, let's say that for our bias values, we'll call it bias of 1 and 2. Okay, so let's do this, right? Let's do this computation. So 0 0.2, 0 0.4, matrix multiplication of 1 and 2 is going to be um, 0 0.2 times 1 plus 0 0.4 times 2. Then 0 0.1, 0 0.2, matrix multiplication 1 and 2 is going to be 0 0.1 times 1 plus 0 0.2 times 2. And so that's weights times inputs. Now we have to add our bias factor, which is 1 and 2. Okay, so now that we do this, right, we have 0 0.2 plus 0 0.8, which is going to be 1, and then 0 0.1 plus 0 0.4, which is going to be 0 0.5. 1, 2. Again, we have to add the bias, and that was going to be 2 and 2.5. So you see kind of what this bias did here? Because before, right, this kind of had a lower value, but because the bias is kind of high, we've bumped up the value. And so now we're like, hey, this, it means a lot. Even if it's 0.5, it means a lot. So we add this bias, and we bump it up. Okay, now we do the sigmoid of this, right? So sigmoid of 2 and 2.5. Now, this notation really just means the same thing as sigmoid of each of the values in there. So we're going to do 1 over 1 plus e to the negative 2. And then we do 1 plus, sorry, 1 over 1 plus e to the negative 2.5. So again, why do I do this? Well, the formula for the sigmoid, right, f of x is equal to 1 over 1 plus e to the negative x. So x is obviously your input, and that's going to be 2 and 2.5. Okay, hopefully that makes sense. And then, right, we have this output layer. So what we're going to do is we're going to connect it here. And now we can have our own weights, which is going to be 0 0.2 and 0 0.1. Again, these are all just random. Like, I just selected them at random. And we'll get more into how we can choose them and how we adjust them later on. But for now, they're just random. So these are now the values of our neurons here. So 1 over 1 plus e to the negative 2 is whatever this is. Whatever is the output of this neuron. And then 1 over 1 plus e to the negative 2.5 is the value of this neuron. So those are now acting as our inputs. Now we have the weights. So let me try, see if I can copy this structure. Okay. Then let me also kind of copy this. Okay. Perfect. Okay. So now this is our inputs, right? What are our weights going to be? They're going to be 0 0.2 and 0 0.1. So again, and then our bias, that I don't know necessarily if that layer has a bias. It can. I think it does. But yeah, okay. So what we're gonna do is we're gonna do 0 0.2, 0 0.1, which is our weights. And we're gonna multiply by 1 over 1 plus e to the negative 2, 1 plus e to the negative 2.5. And then we can add a bias, which in this case, since there's one neuron in this output layer, right, we're going to get a 1 by 2 times 2 by 1, and that's going to be 1 by 1, right? So we're going to get one value. So let's add a value. Let's add 1 value to our bias, and so let's add like 0.6. So this would give us the value of 0.2 over 1 plus e to the negative 2 plus 0.1 over 1 plus e to the negative 2.5 plus 0.6. Now, if this is a true output, then we are not going to add a sigmoid function. Instead, we're going to do something called a softmax, which I'll talk about later. But if this is what like is going to spit out your probability, then you don't need to do a sigmoid on this. So we can actually leave it, and this is what we're going to get. Now, if this wasn't your output layer, and it's just, for example, would be hidden layer 2, and so it was not an output layer, then we would add the sigmoid. And so then hopefully you can see kind of what the sigmoid propagation looks like. Okay, now we're going to talk about backpropagation. So the purpose of backpropagation, right, is to improve the network. And so the way we do this is we want to sort of adjust the things we can to make the network more accurate. So what are the things that we can adjust, right? Well, if you recall, right, from the way I was making up numbers, right, there are a bunch of things that we can just sort of make up. And the biggest are the weights. So again, you can think of it as a bunch of as a fancy function fitter, right? And so the weights are the things that we can adjust. Now, can we adjust the inputs? No, we cannot adjust the inputs. And that's because the inputs are kind of fixed, right? Like if we get a handwritten digit of a dime, like that's what we get. We can't really like move this or arrange this in any way to get um uh, a neural network that gives us a better result. So inputs are not things that we can kind of adjust. And then we can adjust the bias, right? So again, I was picking those values kind of arbitrarily, and that's how you know that like we can just create random values and we can adjust those values. So again, I mentioned this kind of fancy function fitter a lot, but you can think of this as not a function of your inputs to get outputs, but it's really a function of, yes, you feed it inputs, but also your weights and your biases. And those weights and biases are actually the ones you can really actually change. So these are your variables. And I would argue that, like in this analogy, I'm kind of stretching it a little bit, the analogy, but these would just be like constants, like, you know, predefined numbers. Okay, so how exactly do we do this, right? Well, the way I want you to think of it is essentially, right, whatever the network produces, right, it produces some value. And so we'll call this y, because again, like, you know, f of x, y, that's kind of how it goes. And so we sort of say, this is like y, right? So y, and we'll call this, we'll put a line for it, and that's line indicates kind of expected. Um, wait, actually, is it expected? I mean, I'm just making this notation up. Usually, I think you may see it in a different way, but actually, the, the bar will say is our network's output, right? So whenever the bar says this is what the network thinks the digit is. So if we feed it a handwritten digit of a 9, we want it to say, oh, it's a 9. But if it says it's an 8, right, then there's some error. So that works out. And then we'll say y is, like the actual expected value. And so expected value for this, right, should be 9, right? So this is like the label. This is like what the image actually is. You can think of it as the ground truth. Um, kind of. This is not an observation though. It's a prediction. Like it's what we think the handwritten digit is. So again, this is more like a label. This is more like this is what like the image is. Um, so we can kind of think of the error of the model as um, what we expected to get minus what we actually got. So they call this the cost. They call this the cost. And so what you can do is um, for each of the output neurons, right? You can kind of have a cost for each of them, for each like specific instance. So if this was an image of a 9, right? You would want all the other output neurons to be say at 0, and you would want the one corresponding to the digit 9 to be at 100. So then the cost would be like what the actual probability is and what it should be. Um, like this difference between those, and then you sum them up for all the output neurons. And so again, what sort of happens is you can do this again with the weights and then with the biases. But really, what I want you to think about it kind of abstractly as is kind of like a rough terrain, right? Like we have in this picture. And so what we want to do is if this is our constant function. And so if we're here, right, so far with our cost, right, and we have kind of a high error, we want to kind of plot a trajectory, a path to minimize the cost, right? We want to traverse this sort of mountain of cost downwards to an area with low cost. And so, just kind of an analogy, right? Because it may be kind of hard to visualize, is given like x and y, right? If we're here right now with our cost, right, we want to move in a direction to get to lower cost. And so we want to move this way, right? Fall into this local minimum, this critical point. So we want to kind of recognize, hey, we need to sort of move this way on the number line, or this way on the x-axis, to plot a path towards a lower cost. So that's kind of the big overarching theme of backpropagation, which is a way to improve your network. And so how exactly does that work, right? So essentially, right, we're just trying to lower the cost, right? And the way we do that is by seeing how the cost changes. So, for example, right, if, for example, I don't know why I keep on saying, for example, if we have 4 output neurons, and so instead of, you know, digits 0 to 9, right, we're doing digits 0, 1, 2, and 3. So from 0 to 3, um, say we feed it a handwritten digit of a 2, right? And our network outputs 0 0.2, 0 0.3, 0 0.4, and 0 0.1. Then what is our cost, right? Our cost is the difference between what it should be and what it actually is, summed up for all the outputs. So this is going to be 0 0.2 minus 0, because this is what it actually should be. And so for this one, it should be minus 1 because it's a 2. So it should have 100% probability that it's a 2. Now, again, the way I formulated it is as like the expected value minus what we actually got. The orientation, like the order doesn't matter as long as you square them. Because if you square them, if it's a negative number, it'll just be positive, so it doesn't really matter. And you don't have to deal with negative numbers. So we're just gonna square all of these. and then we're gonna add. So we're gonna add. And so that is gonna give you your cost for this sort of example. So now we want to see, okay, we see how the cost is affected by these output neurons, but is it affected by anything else, right? Well, what are these output neurons affected by, right? So if we zoom in kind of on the zero, right, it has multiple other connections to other neurons. And so it's affected by the weights that are connected to them, right? It's affected to the bias that's connected to it. Um, it's affected to the bias that's affected, like connected to this. Um, and like each of these neurons, right, are connected to a bunch of other neurons. So those have weights as well, and those also have biases, right? So again, right, it's a fancy function fitter. So maybe if we tweak our weights and biases, then we can get a lower cost. So how exactly do we like tweak the weights and biases in a way to get lower cost? And so that's the premise of backpropagation. And the way we do this is we need to figure out how the weights and how the biases, again, affect the cost. And so the mathematician you may recognize, right, that this is the derivative of cost with respect to weights, right? Like dy dx, right? It's kind of the same parallel, right? How does the cost change with respect to your weights? So this is kind of what we need to figure out. How does the bias change with respect to, sorry, how does the cost change with respect to your bias? And so what's interesting, right, is, let me zoom a little bit. So in this network that I'm using for reference, and so this is, all these images are taken from Free Blue on Brown, which I think is a really great resource. And I'll link those videos in the Slack, but again, I'll link them again. But Grant kind of shows the number of weights and biases. So you have 784 input neurons, and then you have 16 neurons in this layer, 16 neurons in this layer, and 10 neurons in this layer. So when you sum these up, right, 784 times 16, 16 by 16, and then 16 by 10, right? And then you also multiply by the biases. So there is a bias for the hidden layers, and there's also bias for the weights. I mean, sorry, for the output neurons. So 16 for this one, 16 for this one, and then 10. If you sum all these up, right, you get 13,000 parameters. And so this is the number, you can think of this as the number of variables. So you can change 13,000 variables to try and tweak this to get a lower cost. So there's 13,000 derivatives kind of to take to see how the cost changes with respect to a weight. And you can do that to hopefully lower the cost. Okay, so how exactly does this look, right? So let's just break this down. Right? So your cost is um, your expected value minus the value that you got squared. The value that you got, right, is equal to the sigmoid of your weights times your inputs plus your bias. So if we were to kind of like, you know, work our way backwards, right, um, your change with respect to your weights, right, is really equal to how I mean, your cost with the change in cost with respect to weights is really how your cost changes with your expected value, how your expected value changes with your weights. Right? So this may be slightly confusing. So instead, right, what I'll do is I'll say cost is the same thing, but your expected value is actually a sigmoid of this variable z. And then z is simply your weights times your inputs plus your values. So the reason we do this is just for you guys to see kind of it more simply. And so how does your cost change with respect to this? Because this is the expected value. This is the value you got. You can't change the expected value. You can only change the value that you got. So how does the cost change with the value that you got? Well, um, that changes with respect to your z, right? Because the value that you got is simply the sigmoid of z. So if you change z, then you change the value that you got. And then z is affected by your weights. And so if you were to do this right, you would find that this is just chain rule. And so um, you would see that, hey, this is how your class changes with your weights. And so this is the essence of backpropagation, right? That this chain rule thing, where you just like work your way backwards. So if that doesn't make sense, right? Think of it as things in a number line, right? So change in cost, right? You can think of it as being on a number line. So we can either move it left or right. And if we move it left or right, it's going to move the activation value, which is what Grant uses as his notation. But if we change the cost, like for me, for us that would be like the value that we got, right? But if you move the cost, right, you move the activation correspondingly. If you move the activation correspondingly, you move the z value correspondingly. And then if you move the z value correspondingly, then you move the weight correspondingly, right? Or you can leave it in the other direction, right? If you move the weight some little nudge this way, then maybe it's going to nudge your z value this way. And if you nudge the z value this way, then maybe it will nudge your activation value um, to the right a little bit. And if you do that, then maybe hopefully you'll get a lower cost. Okay, so what is the point of calculating all of these derivatives? Well, just hold on that, right? Let me go over exactly like numerically what this looks like, right? So y minus expected value, that's what you got, right? That is cost, and that's really a function of the value that you got. The value that you got is sigmoid with respect to z, right? And then z is equal to weights times inputs plus values. So So these are partial derivative symbols, and that's just because if we're dealing with a multivariable function, which then you want to keep the other variables constant, and you just want to take the derivative with respect to only your variable. So that's why I have these sort of like partial derivative variable notation. But again, right, how your cost changes with respect to your weights is how your cost changes with the value that you got, times how the value you got changes with respect to z, and how z changes with respect to the weights. So this is just chain. So um, if we were to take the derivative of this function, right, that would be 2y minus y bar. So derivative of your cost with respect to the expected value. All right, so derivative of the cost with respect to the value that you got is just 2 times the expected value minus the value that you got. And then the derivative of the value that you got with respect to z is just the derivative of the sigmoid of z. And then derivative of z with respect to the weights is just uh, derivative of z with respect to weights is just the inputs. Or um, this is the activation of the layer previous. So this is just notation. Like these just mean the same thing. But if you think back to like our examples, right, that we did, um, right, we fed these, right? So like in this calculation, right, we do weights times inputs times plus minus. And so the inputs, right, would be the values of these neurons. And so we call these neurons the values of these neurons as activation values, right? Or activation. And so if we say that, hey, this is layer L, right, then what our inputs are just like the activation of the layer previous. So activation of L minus 4. So that's just notation stuff. That's just to match up with what Grant says. But simply, right, derivative of z with respect to weights is just your inputs. So that's what that is. Okay, so that's like concretely what we're trying to, like, what the chain rule does. So if we multiply all of these together, right, then we can see how your cost changes with respect to a weight. That's it. Okay, so what exactly is the points, right? Well, some of you may have heard of or know about the gradient, but the gradient, right, gives you the direction of steepest ascent. So then the negative gradient is just the opposite of that. So it gives you the direction of steepest descent. So positive gradient is going to say, hey, this is how you go upwards the fastest. Negative gradient is this is how you go downwards the fastest. So again, right, if we're trying to traverse down this coast mountain, it would be nice to know the direction of steepest descent, because then we go down, down, down the coast mountain, right? And so that's why we compute all the derivatives, because um, the gradient of our fancy function, right, with the weights and biases, is just, a huge matrix of how the function changes with respect to weight 1, with respect to um, as ugly how your function changes with weight with respect to weight 2, and so on. So that's why we do this chain rule business. That's why we calculated these, because our gradient is just this. So the negative gradient is just you just multiply by negative. And don't forget the negative. If you're implementing this, don't forget the negative. It will be very painful to debug this. Okay, so um, that's pretty much it. If you if you want to kind of um, pause this and sort of process this, you can. What I'm going to cover now is sort of just like this in more notation, and how we do this for the entire network. So we kind of generalize this concept. So this is sort of an optional slide. So if you want to head off, you're welcome to do that. All right. So this is kind of the bonus section, but this is how we kind of do this for all of the neurons in the network. So how we do back propagation for all the neurons in the network. So again, right, the cost is the sum of the activation values that we got minus what they should be squared for each of the neurons in the output. So what does this actually mean? Well, this is 0.83. If we expected 1, then this would be 0.83 minus 1 squared. So has an activation value of 0.63. So if we expected 0, then we'd square it. And so then the cost would be the sum of these. So we'd add them. So that's our cost. Now we have an activation. So they use this L superscript and this J subscript. So this L superscript just indicates the layers. So in this notation, right, L is this layer. And then this layer would be L minus 1. And then J just is that the subscript just indicates like kind of the neuron um, in the layer. So this would be A0 because it's the first neuron. So we start indexing at 0, and then this is the second neuron, and so this would be A1. So the activation, right, of anything is just the sigmoid of the z value, right? And so this is just a variable that we use to just simplify the equations a little bit and kind of separate them a little bit. But the sigmoid would just be, again, sigmoid of weights times inputs plus biases. It's the same thing. It's just now we're saying, hey, C is equal to weights times inputs plus biases. So the z variable, right, with um, with respect to a given neuron is all of the weights connecting that neuron to the neurons in the previous layer, which is what this k means, times the activation values of the previous layer. So again, um, with this, right, you would say, okay, um, the z value, right, is the weights connecting from j to k. So in this case, right, we only have one, and then we'd want to multiply by this specific k's activation layer, activation number. So yeah, this is just k because we're only connecting this k to this j. So um, we have the weight connecting j to k times the activation of k, which is 0.4. So again, activation is just like the value of the neuron. So this is 0.4. And then we'd add a bias to this, and that would be a z value. Now, if you were to do this for all the variables, right, then all the neurons in the previous layer would be the same thing, right? This wouldn't change, and this wouldn't change, but your z value would change. So your z for a given neuron, right, would be the weight connecting from J to L minus 1, which is all the neurons in the previous layer, times A L minus 1. And actually, to simplify the notation just a tiny little bit, right, um, write it like this. So we're going to sum um, from I equals 0 to I equals the number of neurons in layer L minus 1. And so for this case, right, L minus 1 is going to be 3 neurons. So it's going to start here, and then it's going to go down with this summation. So ideally, right, these would all be connected, right? Each neuron is connected to each of the neurons in the next layer. So what we do is we'd have a weight connecting from node J to I times the activation, so the value of the neuron from the previous layer, I minus 1, so this layer of the ith neuron, right? So you can think of this as your weights times your inputs, except the weight is from J to I. It could also be I to J, like it doesn't, like the direction doesn't mean anything, times the activation of the previous layer's neuron, right? Um, plus the bias. Um, and so this bias would be kind of outside the summation, because it's added at the end. I mean, it could be inside the summation, but again, like you would sum up like the same bias over again, so that's the same thing as just adding it outside the summation. Um, but that's how you get Z. And so then you would just do your same chain rule to get how Z changes with respect to the weights on this sort of function. Um, and so like how to do a chain rule, how to do a derivative in this, like it's just you could just write this out like fully without the summation for all the terms, and do the derivative like that for each of the terms. I mean, you wouldn't do this by hand; the computer would. But I'm just saying, mathematically, this is like what we would do. Okay, so finally, right, we want to also find out how your cost changes with the previous activation layer. And the reason you do this is because you don't just have one set of weights, right? These are each connected to a bunch of nodes in L minus 2, right? And you may have even more layers like that. So you want to see how the cost changes, not with respect to the activations of this layer, but with this layer. Like you would want, the formula for that, because then you go backwards for all the layers that you have. Okay, so now we want to calculate how our cost changes with the layer previous. Right? So how exactly do we do that? Well, what you sort of have to realize is, again, we kind of have to bring up the summation, but let's work backwards, right? So we want to see how the cost changes with respect to the activations of the previous layer. So instead of how the cost changes with activations from layer L, we want to find how the cost changes with respect to the activations from L minus 1. So first, right, the cost change with respect to layer L. Then activations of layer L change with respect to Z. Then Z changes with respect to activations of the previous layer. So it's the same thing as I mentioned above, except instead of with respect to weights, right, it's actually with respect to inputs. And the inputs are the same thing as the activation values. So again, right, as we described like earlier, right, in this slide, um, like these are the same, except we don't want the derivative of z with respect to the weights, we want it with respect to the inputs. So then it's just going to be dz with respect to the inputs, which is just your weights, right? So that's the derivative of this with respect to the inputs. So it's just going to be your weights. And so with this, right, there's multiple like activation values that contribute to the activation values of the previous layer, right? Like this neuron is input to this output neuron and also this output neuron. So it has two. So what you do is you would find change, right, with respect from activation of L minus 1. Sorry. Um, you find change of the cost with respect to activation of L minus 1. Um, and you do like through this path, and then you do through this path, and then you'd sum them up. So you do the sum of the changes with respect to like uh, each of the paths. So this would be from, let's say, j equals 0 to the number of neurons in layer L. And so you'd say the cost with respect to AJ on layer L times AJ with respect to the Z value times the value of Z with respect to the corresponding activation. So again, these are just your inputs. So you just add them up. You just add up, hey, you know, this this neuron is affected, this much by this activation and this much by this activation. So then you just add them. And so that's sort of the formula. And then again, if you have the change in cost with respect to this layer, you would just do the same process for this layer. If you have the change of cost with these weights, then you'd find the change in cost with respect to these weights. Then you'd work your way backwards all the way to the start of the network. And so you find the negative gradient, and you would take your weights, and you would add, we'll call it like a gamma of the negative gradient. So you don't want to have the full negative gradient because that'd be kind of big, but you just want to add like a small um, step. So you'd take a small step in the direction of steepest descent, and you'd continue in the direction of steepest descent with this negative gradient, and you'd slowly climb down this constant mountain. So that's what we're doing with backpropagation, and that's like the math behind it. Um, I know it's a little bit tricky, and I just wrote down a bunch of derivatives. So if it doesn't make as much sense to you, check out the 3 Blue, 1 Brown videos. Those are really good. And stay tuned for the next parts of this lecture series. All right, I'll see you guys.